I'm Eric Nordmark. I'm the CTO and co-founder at ZEDEDA. And yeah, there were some questions earlier about security and why aren't you talking more about security? Well, I'll let you in a secret. I can talk for hours about it. I'm not going to do that today. But I'm going to try to summarize what is actually the essence of this, right? So my background is basically building systems, and at some level that's building robust and secure systems out of fallible and insecure parts, right? So how do you actually make the whole system work? And that's a theme in all of this. So what are the security challenges at this distributed edge that we talked about earlier, right? Well, and this is in addition to all the things you already know and love in the data center in the cloud, right? You need to deal with, there you have multi-tenancy, users, roles, whatever, right? Software supply chains, lots of concerns over there. Those exist here as well, but there's a set of things that are unique, right? One is that the locations where these things are deployed is actually more distributed. You might not know, about what's the network security at that location. You might not have the same level of physical security because it might be sitting under the counter in the retail location or on the factory floor or whatever. And the apps that you want to bring out that you've been running in the cloud, right? Your containers, whatever, they typically assume both, right? Because they've been written with somebody who's focusing on the application logic, not actually focusing on these infrastructure pieces, because Azure, AWS, et cetera, they actually provide those pieces for you. And the other piece is that, well, as you go deploy this, you actually need to provide both an infrastructure layer so that you can actually go deploy it on these boxes, have to run around to grab the boxes, and so I can show them in front of the camera, but you deploy these boxes, right, Intel, ARM, whatever, you need to worry about both the physical, device, the network, whatever, being compromised, as well as something that's more about the application, right? Can someone get access to the application data and steal that, corrupt it? The other thing that you have to worry about out at the distributed edge is connectivity. Well, is connectivity a security issue? Well, it is from the sort of network security, but that's nothing new, right? You have firewalls, whatever. But the other part of it is that many of the security solutions you might assumes that there's someone there helping you, doing some form of attestation, remote attestation. Well, how do you do that when the network is down and you're not going to have network connectivity for an hour, a week, because you're on a truck in the middle of the jungle doing oil exploration, right? So how does you get the stuff to actually work? As you deploy this stuff at scale, you might be concerned about not only about can people attack me, but can I become part of a botnet, right? We've seen this stuff with consumer IoT devices a number of years back where they took out a significant part of the internet, right? Just from doing distributed denial of service attacks. So that's something that you might have to worry about as well. You might have that in the data center, but again, they have the tools, they have the intrusion detection systems. You don't need to worry about that to the same extent if you're trying to deploy the solution. Another one that's a bit subtle is, in many cases, so we have sort of OT concerns and IT concerns playing into this. In many cases, it's actually the same organization, company responsible for both, right? The guy we showed earlier that has 6 or 8 arms, right, trying to manage this. But in some cases, actually independent entities. Some people we talked to earlier talked about deploying imaging equipment into hospitals. Yeah. Hospital runs IT security. It's very strict. The people that sell the X-ray machine, they don't care. They don't even talk to those guys. They sell it to the radiologist, right? And they drop in this box. Do they know anything about the network security in that system? No, right? Same thing with deploying these servers out at dealers in the automobile industry. The dealers have some networks with people with laptops. The people that want to push these firmware images out to cars, they don't know what that is. They can't necessarily assume it's there, right? They have to worry about making sure that their solution both works, meaning it can communicate, as well as being secure enough for their purposes, right? Because they're responsible for their part of the solution. So concretely, when you drill down into this, you have, can people, go plug in a USB stick? Can you go and flash the BIOS with your own copy of the BIOS? Steal, duplicate disks, right? A bunch of things around physical security, in addition to all of the other things you've already know and love. So that's sort of the context of what we think you have to think about when you're doing security at the distributed edge. Everything you knew from before, plus a bunch of new things. And the other thing that people might think about is, hey, wait, we already know how to do this because we do it on these devices, right? These things are very different because there's assumed to always be a human being in front of them. And that you don't have here. So we never built this. So sometimes when people talk about security for industrial IoT, they say, oh, we do TLS, right? Well, sure, TLS is great. We use it. But it's just a tool, it's a building block. What does it mean to actually have a solution, an actual system that works, right? So all of these things about X509 certificate, their format, disk encryption, trusted platform modules, trusted execution environments in hardware, measured boot, secure boot, role-based access control, two-factor authentication, vaults, firewalls and access control lists, operating system hardening, hypervisors, container isolation, right? These are all building blocks. They actually are critical to building the system, but they're not the system, right? So this is very important if you actually want to have an all-encompassing system. And one of the reasons that we managed to attract a bunch of these users and large customers is that they care a lot about this stuff. They need to worry about the whole picture, make sure that the system is secure. So the third piece in this is what pieces are actually worth protecting. So if you look at the way people do a laptop, a common way is saying, yeah, you do full disk encryption, right? And then you do whether it's a fingerprint or you need to log in to unlock the disk, right? That's a great technology, right? But it assumes that there's always a user in front of that thing logging in with some form of credentials. So it doesn't work here. So to do something that fits at this edge that is largely unattended, you need to have a different mechanism. So you need to understand what are the constraints, or what are you trying to do? And it turns out that we're booting this operating system, EVOS, right? That's open source. We don't actually care about somebody reading those bits because they can go read the source code as well. But we care about the integrity of it. So we need to validate the integrity of that. But that's all we actually need to do. When you look at the applications that are being deployed on this stuff, whether they're virtual machine images or whether they're containers, OCI containers, whatever, right? Well, the application itself might be intellectual property. It's a secret sauce for doing oil exploration, right? It might run with a cloud in it or container environment variables that contain credentials, certificates, other things that you care a lot about, right? And it might produce data that is actually highly valuable to you, right? You don't want, whatever happens, you don't want to lose any of that, right? So there you clearly need to have both integrity and confidentiality. And that's sort of a key thing in terms of understanding what problem you need to solve, right, in the space.
So you're not worried about the OS getting hacked?
Well, no, integrity. You can't change it.
Okay.
But you can read it, right?
Gotcha. Okay.
The other thing that is actually even the other thing that I think is useful is because it's at large scale, right? Is that even if something has been modified in the OS or in the BIOS that you don't know what it is actually useful for the device to come up and call home and say, this is what I look like.
Mm.
Because now you know a difference between, did that happen or did the power supply die, right? And if it's sitting 3,000 miles away, it's useful to know that difference. So that's why thinking about this stuff, and this is all about learning from customers and users, saying, "Hey, what are your problems?" Right? But that's a key thing as well.
Question. So do you have a mode where you can pull secrets from the cloud only upon boot up after it attests to its identity, or do you store secrets on the system itself?
So the way we do it in terms of the technology, so the trusted platform modules, right, whether they're chips or firmware,
Yep.
they have the ability to seal secrets under measurements of the TPM, which have measured all of your boot chain.
Right.
The BIOS, the UEFI partitions, grub, whatever, right?
Yep.
The OS you booted. And that's the technique we use, so that even when you're not connected to the internet, if those measurements are the same, the TPM chip now allows you to get to that key.
Yeah. Otherwise,
Right.
yeah.
But if something changed, you need to go ask somebody saying, is this okay? So I'll show that on a slide in next slide actually after this one. But that's sort of like using these building blocks to make sure that we get the right properties out of the stuff. So the sort of basic thing is, yeah, you want to disable ports that aren't being used, right? And I know that a number of years ago, people said, yeah, the way we do this is super glue, right? You pour it into the USB port. Well, now it's never usable, right? And in many cases here, because these things have, see where I can see one, well, the various serial ports and whatever, right? People might want to use those things, but that's for the application to use because it's going to talk to some PLC controller over a serial port, right? Or the second Ethernet port. So you don't want to pour glue in them. But instead of actually having software control that stuff and having the underlying infrastructure, the EVOS that you boot, not actually use them.
So is it not possible to get to okay, so we talked in the beginning about being declarative
Yes.
about what was happening. So is it not a possibility to be declarative all the way through to the hardware itself and have it designed so it doesn't have the ports?
Oh, sure, but people might want to use them, right? In some cases, in some deployments, they might say, well, we're going to use the serial port or not. So we do that through the policies we actually describe through the orchestration system. So you actually say, okay, the first Ethernet port, right, is actually used to connect to the cloud over the Ethernet, right? And maybe the LTE is used to do the same thing, right? Wi-Fi is disabled because we're not using it, right? And then we might decide that, well, in this particular deployment, we have Ethernet connectivity to PLCs. Another one, we have a serial port to the PLCs. And so they basically specify two things. One is the actual hardware model describing these connectors and their PCI bus, whatever things, right? So you know exactly what they are. And then they describe, when I want to deploy an application, say this application should have access to the second Ethernet port. Or a serial port or whatever. So now you actually have, it's locked down, but it's not locked down from a hardware perspective. But you do actually declare that stuff.
Okay.
And tying together the hardware model and the application sort of deployment.
Okay.
Can you set security? So if you've enabled the USB port, for example, and then you plug a device in, can you set rules at the operating system or hardware level to say the device that's plugged in should look like this? Or is that for the application to control, to say I'm going to reject whatever's just been plugged in, I guess, to prevent, someone unplugging a trusted USB device and plugging in something malicious?
Yeah, that ends up being, if you're giving the USB port to the application, right? Now it's the application that needs to make sure whatever's plugged in makes sense, right?
Yep.
Likewise, if you're giving it, the Ethernet port or Wi-Fi saying, do whatever you want with this, right? Well, it needs to worry about those pieces. But you could have, the only place we can do a little bit more is on the network side, where you can say, okay, you're going to have full unfeathered access to the second Ethernet port, but we're going to put these firewall rules in place, right? Saying it's only the MQTT port from this IP address, and enforce that stuff, even though it looks like you have full access to that Ethernet.
Yep.
The other thing that Raghu talked about is, how do you actually do secure zero-touch deployment here? So there's various people that have tried to do this sort of across the whole ecosystem, supply chain, whatever, right? FIDO Alliance and Intel secure device onboarding, something that they've been pushing for a while here, which is great if it happens, right? But it's very complicated because it involves securely assigning a piece of hardware cryptographically to the next guy down the supply chain. Great stuff. What we did was something that was a lot simpler, partly because we have a simpler problem to solve. It's mostly about saying, okay, we worry about the management orchestration of this stuff, not the applications traffic. So we want to make sure that this particular device can connect up to ZEDEDA in the cloud and basically prove that it is who it's supposed to be. How could you do that sort of out of the factory? And the notion that, and it needs to fit in with what are people used to doing in the factory. So that they're used to imaging devices, right, and not much more. And in some cases, they can do some additional stages afterwards where they do some configuration, right? So, and maybe as part of that, they can extract the identity of the TPM chip in there, right? So depending upon, there's a couple of different forms in here, depending upon the security requirements, as well as what level of flexibility and cost you want to incur with your manufacturer before they ship the device. But fundamentally, it's like a serial number, the hardware serial number that is typically printed on the box somewhere, These ones don't have a barcode, but some of them do. Combined with one unique piece of information that the hardware manufacturer can decide to generate on its own. It's actually in the form of an X509 certificate, but the self-signed one that they can basically say, this uniquely identifies this set of devices, whether it's 10 of them for this customer, whether it's 10,000, right? And using that, you can actually onboard this device with very high security, right? If you actually have fully extracted, in addition to the serial number, but if you boot this thing and you generate a unique device certificate on the box in the TPM chip, private key never leaves the TPM, right? If you can extract that in the manufacturing process, right? And now you can actually ship that thing, that certificate, electronically to your customer. Well, now no one can forge this stuff, right? Because you know for sure these 1,000 devices I ordered, they have these certificates. Those are the only certificates I should actually onboard into ZEDEDA, right? So that gives very strong binding, and then there's some things in between as well. But
question there.
Yep.
Can you describe a little bit who owns that PKI infrastructure? Is that something that ZEDEDA would own, the customer would own? Is that like a multi-vendor ownership?
So good question, because on the previous slide I said X509 certificate format, not PKI. Because if you go read Bruce Schneier, I've been around the internet for a while, and this sort of notion that many of the things that people do with the current PKI, with the 120 root CAs that your laptop and phone trusts, whether you want to or not, right, is not necessarily secure, right? The number of times that people have accidentally issued a bogus certificate for a company called Microsoft, or Microsoft with a 0 instead of an O, right? Like this system is not the best one. The certificates are great. That's all math, right? That defines the stuff. So we don't actually rely on a PKI for the devices at all. They start by generating a public-private key pair in the TPM chip. We create a certificate out of that is self-signed. Now, no one can steal that certificate because its private key only lives in that TPM chip. You can't clone it, right? We then register that in ZEDEDA, right? So we know that this particular device at this particular location has the certificate. We don't need a PKI for that either. If that device goes rogue or someone steals it, from an orchestration perspective, we can, through ZEDEDA, we can say, oh, we don't trust that device anymore, right? Delete the applications, the volumes from it, right? It's gone. Yeah, maybe they already disassembled it, but for none of these things do we actually require a PKI where people need to go buy certificates, right? We don't care about these things being associated with a domain name or an email address. They're just a bunch of serial numbers. So it's actually a simpler problem than what other people are trying to solve.
Yeah. So in this case, we're talking specifically about TPM enrollment process, right?
Yes.
That's the focus. Okay.
And on this orchestrator, right? It's completely different because there it's like, yeah, this is a standard your SaaS solution, right? It uses all of the standard ways of how you do certificates for web servers, with PKI, etc., right? But for the devices, it's actually a slightly different problem. So
what you're essentially doing is establishing a trust of the device. PKI says somebody else is going to tell me who I can trust.
Yes.
This mechanism, you have a non IT, an actual trusted relationship between individuals that establishes the trust of that actual certificate. Your supplier has generated the certificate off the device that they have, and they're shipping the device in one direction and the certificate in another. You've established trust through personal rather than through a central authority.
Yes, and it's also that at some level the identity is a bit ephemeral, right? That at some level the identity of the device, yeah, while bootstrapping it might be the hardware serial number, but after that the identity is really that certificate, right? Yeah. So there's a technique that we've used in some other protocols in the IETF as well over the last decade or so. So I'll touch a bit more on this sort of booting to unlocking applications on the next slide. The other piece that's key here is, yeah, if you're coming from this sort of cloud and very cloud native development, it's all about quickly getting stuff out there, right? You want to enable the developers to actually push stuff. It goes through the CI/CD pipeline. It actually pops out the other end, right? Which is great. And now here we have people sort of from the industrial domain saying, yeah, we operate these things for 50 years, right? And maybe we'll replace the hardware in 7 or 10 years, but you can't change anything, right? And these worlds are trying to meet where they say, no, but we want to roll out new applications, new versions of applications, upsell stuff, right? As well as solving security, delivering security patches. So we need to have dynamic behavior, but we have to be able to make these worlds meet. And you see this stuff in terms of the set of roles that you want to be able to define in the ZEDEDA orchestrator, so that people can both do I'm the app developer part of it, and I have those roles. And then there's some sort of gates as this stuff, more than the sort of usual, canary type pipeline in the CI/CD system, actually saying, well, if you're going to go touch the actual deployment thing, there's an additional check here, right? The people that actually operate that stuff is a key thing. So that's something that is necessary to at least to address this more places where you're at the cyber physical boundary. So the fifth one is something that Raghu will touch upon a bit more, but it is sort of tying in what, given that we built these devices to have this strong cryptographic identity that is tied to a TPM chip, if you have one, right? What can we do for applications? In many cases, applications have similar problems, that they want to securely onboard their application into their own orchestrator or their management system or whatever, right? So and the fact that we can actually be used as a stepping stone to facilitate that stuff is actually a key thing as well, that Raghu will talk concretely about later today. So when we look at and this is a piece that we haven't seen anybody else do, because it is sort of different. The problem is different, right? It's not what you do in the data center. It's not what you do on your smartphone. But when we onboard things, the administrator set some sets of policies, and in some factory you install EOS, right? And that has some hardware identity. It has no passwords. The ports are disabled. You go and deploy the stuff at the field. It runs measured boot, and that measures things from the earliest bootloaders, the UEFI BIOS, etc. Right, a bunch of configuration files, the operating system, and now it has a set of measurements. So this is actually standard TPM PCR stuff, and then it goes through and it does remote attestation. And this is actually, as a mechanism, is fully specified. The Trusted Computing Group did this, I don't know, a decade or so ago, right? Mm-hmm. It's not used that much, but there's some people that are trying to do more of this with your smartphones and whatever, to attest to some website. But here we are feeding these things to ZEDEDA, and ZEDEDA can now look at these things and says, okay, these numbers are good because I can actually go through and do the full validation of it's that version of the BIOS. I know that BIOS manufacturer is supposed to have that SHA, right? This version of EOS is supposed to have that SHA, right? Some other things might be tied into the hardware about exactly what are the hardware components on this board, right? So you might have to say, I want to grab a snapshot of these things in the factory and then check if they ever change, because this particular unit of hardware might have some particular strings for, I don't know, the serial number of the disk controller ends up being measured or something, right? But now you can actually do that, and now once those things have been accepted, subject to this policy, you can say, okay, now you can actually deploy application. Now we can actually send you secret applications, right? Secret configuration data, cloud init data, etc. And as part of that, it goes and downloads the actual content, the images, whatever form they take, and verifies those things. I mean, some of that stuff is standard what you do when you download a Docker container, an OCI container. But we do the same thing for virtual machine images and these other pieces. So, and now you can actually go and run the applications. So that's sort of tying in that, well, now if you boot this thing again and someone has changed the BIOS or built their own version of EOS, which they can because it's open source, right? That's trying to exfiltrate some data. Well, these measurements will not actually match, and this guy will not actually, attestation will not actually complete, and it will actually not be able to unlock the volumes for these applications using these capabilities of sealing the storage root key based on the measurements of the TPM. If things actually change, the attestation ends up saying, okay, I know that you are running the legitimate software, the approved software and firmware or whatever. So we can now actually hand you back the encrypted key you handed to us earlier. Basically, as part of doing this, the device says, I'm going to encrypt this key so only I can decrypt it. Only my TPM chip can decrypt it. I will store it with you. You will hand it back to me when you trust me again, right? But if you don't trust me, don't hand it back to me. But in any case, it's only I that can actually decrypt this thing because it's only my TPM chip that knows how to decrypt this stuff. So this means that you cannot actually spoof the system in terms of getting out this data and getting to these application volumes. So that's sort of the base level of how I can actually ensure that no one can get at the applications by modifying anything in the hardware or firmware or software on these systems. But then you go to this stuff, to the real world, and they say, wait, if you have a power outage, we need to be able to connect to the cloud. That doesn't work, right? Yeah. So how can we do this? Well, there's a bypass here, which is that, well, if the measurements are correct, you don't need to attest anymore, and the TPM chip will let you unseal these keys. So if nothing changed, if you didn't, and change might mean I reposition one of the PCI cards inside this box, right, to another slot. It might be a change, right? It all depends on the BIOS manufacturer. But definitely if you change the BIOS or some other firmware, it's not going to match. But in that case, you need to reattest. But otherwise, you can just go and unlock this data and, the applications just boot even if there's no internet connectivity, which is the critical operational requirement.
So do you, for the supported hardware, I mean, because you don't build any hardware, right?
Yep.
So in the end, you have to keep, a huge inventory of these devices, test all of them continuously every time you update the system to be sure that, there are no issues, bugs, or everything else. So how does it happen and how it impacts? I mean, so if there is a new version of the software before I get everything, deployed to any platform,
yeah.
Because, I mean, I guess that if you are supporting 80 plus devices today, plus all the past, and we have updated hardware every few months, we are talking about several hundred of devices that you have to test all the time.
Yeah, microphone.
We do it in two parts. So the first one is that we have a community supported hardware list, which is community supported, and it gets tested through community. That's one portion, and that might have the problems that you are talking about. Then there is a second portion where it is ZEDEDA certified hardware. And we have our own ADL and everything else. But what happens is when a customer goes in, these are the boxes or devices that they want to keep for a longer time, right? So they actually provide, they get these devices certified, and as part of the certification, we take those devices, put them onto our test benches, and keep running tests against it. Every time we release, we certify a released Eve OS. Eve gets built every 2 weeks. We actually certify a new Eve version every 2 months right now. I mean, these things change over a period of time, right? But every time that happens, we go through and test these things. We have automated, we have built a huge automation suite that can test all of these things. And then there are some that cannot be tested using automation, and where we have people who can actually go ahead and manually do some tests. But they do get regressed every single time we have a new Eve, and definitely also when we have new cloud software that keeps going. So because all the automation keeps running, and that's how we can stand behind and provide support to these devices, because we cannot provide support to things that we do not know of, right? But so, very good question.
And the other part of this is that, we're a relatively small company. We don't necessarily have much leverage with the hardware vendors, but our customers do, right? So in some cases, they will actually, and I expect to see more of this, that they will actually talk to the hardware vendor saying, hey, why don't you guys actually do this, right? And make sure that EOS still works on this thing. So if you have a new version of the BIOS or whatever, right? If you're rolling a variant on the hardware, make sure that it gets tested, right? So I expect to see more of that over time.
Yeah, we have already hardware vendors that are themselves taking EOS in the open source and testing it. on the customer's request, right? The customer asks them, hey, you need to make sure that your hardware in a new version, if you change a chip or whatever on the motherboard, that EVOS works. But I think there's two things. EVOS was made to be very portable because, again, the edge is so diverse. And then there's, of course, the supportability capability where we contract with the customer and the hardware vendor to select the best possible hardware for the use case and provide the long-term support around.
Yeah, but I mean, for some hardware, maybe it's very easy. I mean, some of them are Raspberry Pis in a rugged, configuration. For others, I think that the devices, device drivers are totally.
Yeah. For a software company, we learn a lot about hardware, and in particular, some of the shortcuts some hardware vendors do, and like how did you design this way? And we're trying to educate and help the hardware vendors as well. Like, hey, when you design a new version of your platform, here's some ideas to make your life easier and our life easier, and ultimately our customer's life a lot easier as well. So that's absolutely the case. And we're hopeful that as edge computing continues to kind of become mainstream, that more and more architectures, hardware architectures will be defined, blueprints and reference architectures that will be more adopted by everybody else. You're totally right.
And today, sort of a fair bit of what's being deployed out there are Intel-based systems, which are more uniform, right, in terms of that they actually have a BIOS, and but what we're seeing is ARM has a lot more diverse ecosystem with larger range of price points, I/O connectivity, all of it, right? But it's also a lot more diverse in ways that cause more pain, right? Because you have to go pick up this Linux kernel from some random places, some device drivers over there, build your own kernel and bootloaders, right, to boot on a particular hardware. It's in our interest, our customers' interest, as well as other players like everybody else that wants to run Linux on this stuff. They want to make that stuff be more uniform, right? So I think that we will hopefully make progress on this stuff. For the time being, we know how to deal with that diversity, but it's painful, right?
Do you have any? I mean, so I guess that there are also accelerators in these devices, in some of them, FPGAs, and very, very. So is it the same process in the end, or do you don't really care about the FPGA because it's programmed by the application or whatever?
Yeah. The FPGAs, I mean, for example, this HP device that I have, it has a quad-core NVIDIA GPU, P1000, I think. It's sitting in there. So the way we address FPGAs or like GPUs or any of those things is like you can share them, you can schedule them, but we have to give it to the guest OS or the guest application, mainly because like we cannot have NVIDIA drivers in Eve. NVIDIA wouldn't allow it. Okay, so now we do a PCI pass-through of these GPUs or FPGAs, and then once the guest is done using it, it can release it and it can go back to another guest if needed. Okay, those kind of. So that takes us out of a picture a little bit. It helps us quite a bit too. But then there are some other things where, like especially the serial USB controllers and all of those things that we do have to care about.
So what's the average lifespan of that device that's sitting on the top? Because if you've got 80 devices today, like how many new devices are you supporting each year? And then what's the average lifespan of, say, something like that? So in 5 years' time, what does it look like? Have you got 500 devices to support, 100? And yeah, just out of curiosity, like, are those devices sitting in the field for 10 years? Like, what's the average design life?
This one is supposed to actually last at least for 6 to 7 years in the field. It's definitely supposed to last 6 to 7 years in the field, and it's built like that. Now, the breadth of devices that we have to support in 5 years from now, I do think like it is going to be close to the number that you talked about. And we are doing a lot of work, both in the open source community and also inside ZEDEDA to help that. Tooling, creating things that people can just validate it by themselves. Validation and certification are two different things, right? You validate the hardware by yourself. You don't have to go to somebody else. The full toolkit is available. You don't even have to boot Eve to validate something, all of those kind of things. That is one aspect of it. But the second aspect of it is like actually having the hardware vendors taking over this. And there is a lot of interest from the hardware vendors too, because they want to control the fate of that device, because they want to make sure that this device stays in that field, because that's in their best interest that like this stays in their field like as long as possible. And when it gets to be replaced, then it is them that has to replace it. So they want to control it too.